kiddos. In today's video, we're going to talk about percent error. Now, percent error relates directly back to our conversation or a video on accuracy and precision, because percent error is a way to quantify how accurate we were, okay? So, I mean, in some cases, it might be okay to say, hey, we're pretty accurate, or no, we're not. But what's better than saying that is to say, hey, we were 0.1% away from what the actual value was, or we were 20% away from what the actual value was, so plainly something went seriously wrong. So it's a way to give us a numerical value for our accuracy. There's a relatively simple formula for it. Percent error is equal to your experimental value. Now, sometimes you'll see that called observed. That's fine too, because you might not have done the experiment. Maybe you were taking the information from someone else. The observed value, okay, or the measured value, it could be taken as sometimes, minus the accepted value. Like, what is the real value? So if you remember, we were talking about accuracy and precision in the last video, and we talked about the fact that, hey, you were taking a measurement and your group measured that it was 3.5 grams, but the actual value was 3.0, what your teacher told you. So the value that your teacher told you, or what we would call the literature value, the value that you could look up. For chemistry and physics, for a lot of science stuff, there are actual approved, accepted values kept. There's a big, massive book called the CNC Handbook of Chemistry and Physics. There's also, or CRC, I think. There's also, you can go online and look up those same values. If you went to, say, you know, even a source like probably Wikipedia and looked up the melting point of benzene, it would give you the melting point. That would be the accepted value. What you determine the melting point of that substance to be in the lab is your experimental value. What you also notice is that there are straight lines there, and those of you that remember your math know that straight lines mean absolute value. Generally speaking, we're going to do the absolute value, and we're just going to get a positive value for percent error. That's what will matter most of the time for us. There are occasions, though, where it's actually good to drop the absolute value and just put parentheses there and do it that way, because you might want to know, was my error lower than the accepted value, or was it higher than the accepted value? So the absolute value is most of the time, which will give you a positive answer, but it doesn't have to be. All right, so formula on the board here, okay? Experimental minus accepted, absolute value, divided by the accepted, times 100, that'll give us our answer. So let's look at an actual problem. After lab, you calculate the density of an object to be 28.4 grams per cubic centimeters. The actual density is 30.2 grams per cubic centimeter. You might have looked that up online or in a CRC handbook, or maybe your instructor just said, hey, the actual value of this is 30.2. So how do we calculate then the percent error? So I'm not going to write the whole formula out, but my percent error is equal to the experimental value, which is this, and sometimes it's just helpful just to label. Okay, experimental accepted. So my experimental value is 28.4. Okay, and I'll go ahead and put the units, just because I think that's a good habit to keep yourself in, is of always putting units. Minus 30.2 grams per cubic centimeter, absolute value. Now again, what that absolute value will do is, this is obviously going to give me a negative number. We're just going to drop that negative and go on from there. Divided by, and here's where students often mess it up. It has to be the accepted, the actual value on the bottom. So 30.2 grams per cubic centimeter. Now those units aren't really going to matter because they're going to cancel out. As long as the units of everything you plugged in were the same, everything's okay. But they're going to cancel because the percent error is only going to have units of percent, essentially. Okay, so we're going to plug that into our calculator, 28.4 minus 30.2. I'm going to divide that by 30.2, and then we're going to multiply it by 100. So when I do the first part here, before I do the multiply by 100, because I still have to do that, okay, we get 0.05960264901. I always like to put all this because I want you all to understand why you need to use significant figures, why it would be so ludicrous to write all of that out as an answer. Okay, and then we've got to multiply it by 100, so you can do that one of two ways. You can punch it in your calculator, multiply it by 100, or you can just know, hey, I'm going to shift my decimal place 2 places. Same thing, that's how percents work. And then, so that would give us then 5.960, blah, 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 blah. We need to put that in significant figures, though. So how many sig figs do I need? Well, the 100 doesn't matter, okay, because that's a constant that you're using. But what matters is how many sig figs did your original measurements have. In other words, how precise were they? So they all have 3 sig figs, so that means my answer should have 3 sig figs. So your correct answer then in this case is going to be 5.96%. Now, what you might be asking yourself is, okay, so what does that tell me? Is that a reasonable percent? Kind of depends on the lab you're doing. I think for most of the things we're doing in Chemistry 1, if you're getting a 10% error, that's probably okay. Think about it like a test. If you got somewhere between a 90 and 100 on a test, you'd probably be relatively satisfied. But again, that varies. I mean, I took classes in college where if you had 0.1% error, you would have got significantly marked down. So it sort of depends on what purposes you're doing, what percent of error do you need. And of course, all of this changes depending on how big are these numbers. If these numbers are smaller, okay, then that can make even a really small deviation a lot bigger, okay? And you can tell that you're not that far off. You're 1.5 grams or maybe 2 grams off of a 30-gram sample. What if you were 2 grams off of a 1 gram sample? Well, then you'd be at like 200% error, and that obviously would be an issue. You'll obviously work some more examples of this, and if you need to see some more, maybe I'll put some up in another video, but this is the basics of how to do percent error. Thanks, kiddos.